In 1974, computing belonged to giants, room-sized machines with million-dollar price tags. The corporate gatekeepers decided who could access the world's digital power. Then a $360 chip changed everything. The computer empire never saw it coming. They were too busy counting profits to notice that a piece of silicon smaller than a postage stamp was about to shatter their control forever. This isn't the story of how David slayed Goliath, he just made Goliath obsolete. The machines that processed the world's data filled entire rooms, consumed enormous amounts of electricity, and cost more than most people would earn in a lifetime. These machines weren't personal devices, they were infrastructure, as remote from individual ownership as a steel mill or a power plant. IBM dominated this landscape with the System 370 series, machines that weren't delivered but installed, large steel cabinets with raised floors that concealed thick cables. The air hummed constantly from cooling systems fighting to keep the circuits alive. Buying one meant construction crews, engineers, months of preparation, and a contract that bound you to IBM's ecosystem for years. Digital Equipment Corporation carved out the mini-computer market with the PDP series. The PDP 1170 filled a rack the size of a refrigerator and could cost well over $100,000 depending on configuration. It was revolutionary because it could fit in a single room instead of requiring an entire floor, but it still demanded dedicated operators and institutional budgets. These companies didn't just sell computers, they sold access to computing power through carefully controlled channels. IBM's customer engineers installed and maintained the machines, while their programmers developed and supported the software. DEC provided complete turnkey systems with proprietary operating systems and development tools. Customers didn't own computing power, they rented it along with the expertise needed to make it work. Computing required massive capital investment, specialized knowledge, and trained professionals, so only institutions could realistically afford entry. System operators monitored console displays, loaded magnetic tapes, and managed batch processing queues. Programmers worked in specialized languages like COBOL and Fortran, submitting jobs through intermediaries who controlled access to the machine. Users never touched the computer directly. They submitted punch cards through a bureaucratic process that could take hours or days to produce results. The empire's control extended beyond hardware into standards and compatibility. IBM's System 370 architecture defined how computers should work. Software written for IBM systems couldn't run on DEC machines. Data formats were proprietary. Customers who invested in one vendor's ecosystem found themselves locked into that vendor's upgrade path. This wasn't tyranny, it was simply how the economics worked. Computing power was scarce, expensive, and technically demanding. Centralization made sense because it concentrated expertise and amortized costs across multiple users. The business model was elegant in its simplicity. Sell expensive machines to customers with deep pockets. Provide comprehensive service to justify premium pricing. Control the entire ecosystem to ensure customer dependence. The empire's profits came from managing scarcity, not from eliminating it. By 1974, the computer empire seemed unshakable. IBM controlled roughly two-thirds of the mainframe market, and DEC was the leading force in the mini-computer market. Intel's 8080 microprocessor was introduced in April 1974. The chip came in a small dual inline package just over an inch long and contained roughly 4,500 transistors etched into silicon. It consumed only a few watts of power and cost $360 in single quantities. Compared to the room-sized machines that dominated computing, the 8080 seemed almost trivial. The specifications told a different story. The 8080 could execute roughly 300,000 instructions per second, process 8-bit data words, and address 64 kilobytes of memory. These numbers were modest compared to mainframe performance, but they represented something unprecedented: complete central processing functionality in a single integrated circuit that individuals could afford to own. Intel designed the 8080 as an improvement over their earlier 8008 processor, addressing the limitations that had restricted the earlier chip to specialized applications. The 8080 featured a more flexible instruction set, faster execution speed, and improved system integration, though it still relied on external chips for clock generation and bus control. Most importantly, it featured a 16-bit address bus, allowing it to directly address 64 kilobytes of memory with far fewer support chips than its predecessor. The chip's architecture was radically compact. Where mainframes required cabinets full of circuitry, the 8080 compressed the core processing logic of a computer into a device small enough to sit in the palm of your hand. The brain of a general-purpose machine had been reduced to a component. Intel's marketing positioned the 8080 as a component for embedded systems and industrial controllers. The company's literature showed applications like traffic light controllers, electronic scales, and automated test equipment. These were logical extensions of Intel's existing microprocessor business, serving customers who needed computing power for specific control functions rather than general-purpose data processing. But the 8080's real significance lay in what it made possible rather than what Intel intended. For the first time, individuals and small groups could build functional computer systems without institutional approval or corporate budgets. The chip provided the processing power. Standard memory chips provided working memory. Simple interface circuits connected keyboards, displays, and storage devices. Everything needed to build a basic computer could be purchased for a fraction of the cost of a mini-computer. It wasn't just a controller for machines. It could execute real programs, follow branching logic, handle calculations, and respond to external signals. For the first time, the core behavior of a general-purpose computer could be purchased as a single part. The number that mattered wasn't performance. It was $360. That price didn't just lower the barrier, it shattered it. Failure became affordable. Experimentation became possible. Ownership became realistic. The chip's availability through normal distribution channels dramatically lowered the institutional barriers that surrounded mainframe purchases. Electronics distributors stocked the 8080 alongside other semiconductor components. No sales presentations, credit approvals, or service contracts were required. Anyone with access to an electronics distributor could purchase the components needed to build a computer. The 8080 enabled hands-on exploration in ways institutional systems never could. Hobbyists could modify hardware designs, write custom software, and explore applications that would never justify mainframe time. This freedom to experiment would prove more valuable than raw processing power. The giants saw the 8080. They simply didn't see a reason to care. Because the empire's business model was optimized for service contracts, which generated recurring revenue that often exceeded hardware profits, these companies measured success in terms of large deals with sophisticated customers who needed comprehensive computing solutions. Within a year, the Altair 8800 signaled that a new market was forming, though the empire didn't recognize it immediately. It's a small company in Albuquerque, New Mexico, announced the Altair in the January 1975 issue of Popular Electronics magazine. The machine was built around the Intel 8080 and advertised at $397 as a kit and $498 assembled. It had no keyboard, no display, and no storage system. Programming required toggling switches on the front panel to enter machine code instructions. By conventional standards, the Altair was primitive. It couldn't run business software or support professional applications. The user interface was incomprehensible to most people outside the electronics hobbyist community. But it was a complete computer that individuals could own, and that made all the difference. The Homebrew Computer Club formed in Silicon Valley in March 1975, bringing together engineers, hobbyists, and entrepreneurs who shared an interest in personal computing. The club's meetings featured demonstrations of homemade computers, discussions of technical improvements, and informal trading of software and hardware designs. Much of the early Silicon Valley personal computer movement emerged from this community. The empire's executives didn't attend Homebrew Computer Club meetings. They focused on Fortune 500 customers, government contracts, and university installations. The hobbyist market wasn't worth their attention. Even if every member of the club bought a computer, the total revenue would be less than a single mainframe sale. From their perspective, they were right. Payroll systems processed thousands of employees. Government databases held millions of records. Research simulations demanded enormous power. The 8080 couldn't meet those requirements at institutional scale. The Empire's technical staff understood the 8080's limitations better than anyone. IBM's engineers had access to some of the most advanced semiconductor research in the industry. They knew exactly how much processing power, memory capacity, and I/O bandwidth were required for serious computing applications. The 8080 fell short of the performance levels required for large institutional workloads. The Empire focused primarily on institutional competitors rather than semiconductor suppliers. IBM tracked DEC's minicomputer developments. DEC watched IBM's mainframe announcements, but Intel was a semiconductor supplier, not a computer company, so their microprocessor developments weren't considered competitive threats. The Intel 8080 didn't destroy the computer empire through direct competition. It began shifting relevance away from their centralized model by enabling a fundamentally different relationship between people and computing power. The change wasn't immediate or dramatic. It was gradual, structural, and ultimately irreversible. Personal ownership transformed computing from a service into a tool. Mainframe users submitted jobs and waited for results. Minicomputer users shared resources through time-sharing systems. But 8080-based computer owners had direct, immediate access to their machines. They could experiment, modify, and customize without asking permission or justifying their actions to system administrators. The Altair 8800 demonstrated that complete computers could be built around the 8080, but it was primitive and difficult to use. The real breakthrough came when entrepreneurs began building more sophisticated systems that retained the 8080's accessibility while adding practical capabilities. Companies like IMSI, Processor Technology, and Chromemco offered improved versions of the basic 8080 computer with better interfaces, more memory, and professional construction. Software development exploded around the 8080 platform. Microsoft's first product was a basic interpreter for the Altair, written by Bill Gates and Paul Allen in 1975. The program allowed users to write and run programs in a high-level language without understanding machine code or assembly language. BASIC made the 8080 accessible to users who weren't electronics engineers. The CP/M operating system, developed by Gary Kildall at Digital Research, provided 8080-based computers with sophisticated file management and program execution capabilities. CP/M allowed users to store programs and data on floppy disks, run multiple applications, and manage complex software systems. For the first time, microcomputer users had access to capabilities that approached those of small mini-computers for certain tasks. Then software followed the hardware. Word processors replaced typewriters, spreadsheets replaced ledger books, databases moved from climate-controlled server rooms to office desks. The tools that once required institutional approval now ran on machines individuals owned. And once the door was opened, it could not be closed. Faster chips appeared, cheaper designs followed. Innovation accelerated beyond the centralized control the industry was used to. What had once been a managed industry was becoming an ecosystem. The Empire's institutional customers began noticing microcomputers as their capabilities improved. Small businesses that couldn't afford mini-computers found that 8080-based systems could handle their accounting, inventory, and word processing needs. Engineering departments used microcomputers for design calculations and data analysis. By the early 80s, large corporations were purchasing microcomputers for individual employees rather than expanding their mainframe installations. Even systems built on competing processors proved the same truth. Computing had moved from the machine room to the desk. The idea unleashed by the 8080 had escaped its creator. The Empire's early responses failed to match the momentum of the microcomputer movement. IBM introduced the 5100 portable computer in 1975, but it drew heavily on IBM's mainframe and minicomputer heritage, running APL or BASIC from ROM rather than embracing the emerging open microcomputer model. DEC's VT78, introduced in 1978, was essentially a PDP-8 minicomputer in a desktop package, but it retained the minicomputer's complexity and cost structure. These products acknowledged the microcomputer threat, but didn't address its fundamental advantages. software compatibility became a growing strategic vulnerability. Decades of investment in proprietary operating systems and applications became liabilities when customers could achieve similar functionality using standard microcomputer software. The empire's software advantages were neutralized by the microcomputer industry's rapid development of compatible alternatives. As computing became personal, the empire's institutional focus became a constraint. Departments that had waited months for mainframe access could solve their computing problems immediately with desktop systems. By 1981, when IBM introduced the personal computer using Intel's 8088 microprocessor, even the empire had adapted to the new reality. The industry's momentum had shifted. The IBM PC used standard microprocessor technology, ran third-party software, and could be purchased through retail channels. IBM's entry into personal computing marked a turning point, confirming that microprocessors had silenced the old model of centralized control.